Okay, so this is the optical sky all of us are very much used to. And if I were to show you the exact optical radio sky for this region, it would look quite different. And that's why we need to look at all wavelengths to understand various objects in the sky, especially the extragalactic ones, because some of them might be more enigmatic, more energetic, showing us more things which we often miss. So this is an attempt to show you how it would look if we superpose the radio and the optical. So the red emission here is from the radio. What you see is a radio galaxy, but a special radio galaxy, and that is the topic which I'll be covering. So this is how a typical radio sky would look if you were to have radio eyes, or if you have a radio telescope and make good images. And here we have now almost all the sources except that supernova shell, what you see, all the rest of the sources are radio galaxies powered by supermassive black holes giving out jets. Some of them are resolved, some of them are not resolved. So I'll just give you a brief introduction about the radio galaxies. So typical galaxy looks like this, has a scale of 30 kiloparsec, but a radio galaxy extends much beyond the 30 kiloparsec. It has AGN sitting at the center of the galaxy, powering this bipolar relativistic jets seen at radio wavelengths, which often terminate into radio lobes and hotspots. That's the general anatomy of the radio galaxy. And these come in all shapes and sizes. And radio astronomers have classified them based on their property, shapes, their spectral colors, so that we understand what is their what are the parameters for their growth and evolution. And this is a simulation of how a continuously injected radio galaxy would look in real time. And that's what the power of supercomputers allows us to do. So this is just a plain hydrodynamical simulation showing the same. And like I said, in the blue image which I showed, the resolution is very crucial because you were not able to resolve what is, you are only seeing the point sources. And with better radio telescopes, by better I mean in radio astronomy, we use a technique called interferometry, which allows us to get very good resolution. And this is an example of it. This blob-like structure is actually much more complicated than we can think of. And you can see at various resolution how we can understand, okay, it's not probably one source, but a combination of two sources. So I'm just putting out this concept in at the start so that later on you get the context. So radio galaxies come in two flavors, basically FR1 and FR2, named after the two scientists, Panaroff and Riley, who actually identified this classification. The FR2s are more powerful, where the jets are seen to go to kiloparsec scale, end in bright hotspots, very energetic. And the FR1s are brighter at the start, near to the galaxy, and then they don't really form hotspots. They actually fizzle out. So these are the two very good examples of the same. And like I mentioned, the extent of these radio galaxies is much more beyond a normal galaxy scale. And you can see some radio galaxies can go to grow to megaparsec scale, and megaparsec is quite big. Can actually fit 33 of the Milky Way if you stack them in a line. So the special class I was talking about is the giant radio galaxies, which are the largest radio galaxies growing to megaparsec scales. They can extend up to the scale of galaxy clusters. And they mostly have this FR2 type of radio morphology, telling us that they are really powerful because that's the FR2 class compared to the FR1. And there has been an effort going on to understand why they are big, why they are rare. And recently we put out a review based on the recent results from new surveys. So some open problems, like I mentioned, we are trying to understand why they are so big, how are they formed, how rare are they, and are they simply old? And what can we learn from what astrophysical processes contribute to it, or they contribute to? And we are trying to probe these kind of things for this class of giants. But one of the main things which has been neglected is the restarted activity, which is what I'll get to next. So restarted activity is one plausible model put out to explain why they could be big, because they could be starting, stopping, and the cycle must be going on. But prior to that, the two big models which actually are quite famous are the environment and the AGN. Like if you have a very powerful AGN, which is pumping out jets or energy for a long time, it can really make the radiogalaxy big, and it can be partially supported by its location in the cosmic web, where it is encountering less resistance from the environment, thereby allowing it to grow to larger and larger scale. So we think it's probably a combination of the two. But to probe, we need more data, more number of giants, because as I said, compared to the radiogalaxy population, they are quite rare, total radiogalaxy population. Anyways, coming back to radiogalaxies. So, like I mentioned, they come in various shapes and sizes, and based on what we have studied in the radio and optical, we have classified them into various categories. And this actually tells us a picture that these various shapes and sizes and their properties are actually, we are probably catching them in various phases of radiogalaxies lifetime. So like I mentioned, the restarted, where you see two distinct set of lobes, the inner and the outer. And sometimes if you go to very, very fine resolution, you see that a point source inside hosts a double again. So those are the categories. Sometimes they manifest into X-shape, where the lobes are, there is a backflow from the lobes hitting onto the host galaxy, and the host galaxy more denser medium is pushing it away from the straight line joining the two lobes. So the point I'm trying to drive here is that together, if we study these various shapes and sizes, classes of the radiogalaxy, there is a picture to be seen. And that's what a model which has been proposed, that the radiogalaxies start really small, and you can see the direction marked in the arrow, and see these, you can ignore the acronyms, but it's like they start really at the top with a lot of power, smaller in size, and as they grow, there is losses. The sizes keep on increasing, and then you can then split out. Okay, based on their time scale and the sizes, we can then try to understand. Okay, where are these classes lying on this plot? So this is basically called the power diagram, PD plot, power and distance. But distance here means the size. So the restarted is again here, and that's the main thing which we want to talk about. Okay, so restarted, on the left, what you see is a typical restarted radio galaxy. On the right, what you see is also a restarted galaxy, but that we call as double radio galaxy, DDRG. Because there you see clear morphological signs in the radio that okay, there was AGN activity which stopped and then it resumed again. Whereas on the left, you don't really see, if you see, what you see is not a radio image as such, but it's a spectral index image, which one creates using combining two different radio images at different frequencies. So it will become more clearer. But here you can see, note down the numbers 0.8 or 0.4. 1.4 refers to the spectral index value of an older plasma, and 0.8 is like a freshly injected plasma. Now this will make more sense once I show you more plots. But basically, DDRG is a subclass of restarted radio galaxy, and that DDRG allows us to study it more. Historically, this was coined in 1977. But this was sort of a misclassification because they didn't have the entire deep data to understand what was really going on. So recently with MeerKAT, this is the same galaxy now seen. The red is all radio emission. You can see that what they thought of is double and double is actually a continuous stream of plasma which is going on. And it's very difficult to classify this particular galaxy into one of these categories, like is it strictly double or FR1 or FR2? So there are some hybrid classes like this, and we are getting more of these with new sensitivities available to us. So the main DDRG class was identified and studied initially by Schoenmakers in his thesis around about 24 years ago, where you can clearly, distinctly see two sets of radio lobes. And what you see at the very center is the core. That is where the host galaxy or the supermassive black hole sits. So this is one example, and that's his main seminal paper on where he coined that word, and then more studies followed. Like I said, shapes and sizes. Here is another example. This on a bigger scale image, you can see it is egg-shaped. But if you have a higher resolution available, you can see the bright radio core. If you probe inside it, there is a double source inside it. So what is that telling us? It's telling us that there is a restarted activity which is going on, and in the past there was more activity which actually extended into this kind of shape. So what have we learned so far from only the 70 odd objects which have been identified, and even fewer were studied in detail? That the jets do not continuously power in AGN. There is a stop gap or stop and start mechanism at play, and we are trying to understand why, under what condition it happens so. And this is the only class of AGN or radio AGNs where we can clearly see restarted activity because of the morphological evidence. Unlike in other AGNs, it is very difficult to understand whether it was active in the past or not from the optical or IR studies. The newer set of jets actually propagate or expand into a medium which is previously evacuated by the previous jet activity. So they most likely experience less resistance to grow. The outer lobes, if it has been a long time since it has been injected by the jet, they will fade away. And often that means if you don't have a sensitive radio image, we might be missing many of these. We might be just seeing the inner ones. Outer ones are too old or too diffused for us to observe. So we need very deep radio observation, and that is why in last 10 years, more of these objects have been found because of the sensitive observations coming from LOFAR. So like I said, this class offers us a good lab to study the duty cycle of the AGN, and the start and stop. It could be because of the fueling. The AGN could be starving at one point, and there must be some merger which might be bringing in the fuel for it to accrete onto, and then the AGN activity would begin. So these are like ideal places to look at to probe this kind of aspects in for the AGNs. So how and what aspects to study, what we can do from the radio? It's like we need to do multiple observations to get the radio spectra, to understand which part of the radio plasma is older, which part is newer, and by how much, what is the duty cycle, and like the inner and outer, like I mentioned. And then there is injection index and duty cycle, which I'll come to in a couple of slides. So basically for this, we need multi-frequency data. We need to study not at one radio frequency, but multiple radio frequencies. So why is that so? So typical radio spectrum or radio synchrotron spectrum looks like it's a power law, what you see here. And that's the equation which mainly governs it, where flux frequency and the spectral index are defined. And you can see on the right top various components. That's again a DDRG, but a asymmetric DDRG. So like I said, hotspots are the brightest, so they're continuously getting injected. Hence the spectral index is flat, that is 0.3. And the lobes, where the losses are more, you can see it is much more steeper. Now the idea is to get spectral index information for every pixel in the image. Okay, and for that you require really deep, very lot of multi-frequency data to determine that. Once we do that, so this spectrum, power law spectrum, basically as the plasma is aged or it is older, firstly, there are radiative and adiabatic losses which are happening, which leads to a break in the spectrum. And this break will go to more lower frequency when a lot of time has elapsed. So the older the plasma, the steeper the spectral index and lower the break frequency. So in other words, a newer source or a younger source will have break frequency at very higher frequencies. Okay, by higher I mean gigahertz frequencies. But if it's a really old source, it will have very steep spectral index and its break frequency will be on the scale of megahertz, like 200 megahertz or 100 and so. So this is the motivation for us to study these classes of sources at multiple radio frequencies. You need to observe with various telescopes around the world to understand, okay, what is actually the spectrum, and that's quite hard to do. So here is an example of a source. You can see the number of telescopes listed. So all the way from Australia, South Africa, India to the VLA, we need to combine all so that we have all these data points, and then we can go on to spectral modeling and then determine the break properly. So these are the three main models which we actually try to use to fit various parameters like what is its radiative or spectral age and how long is there a mixing of old and new plasma and such. So like I said, only 70 or so have been reported until 2017, these objects, and now 130 or so are known, and handful objects, less than 10 or 5 objects have been studied at this multiple frequency to determine what is the age of the inner and the outer, what are their properties, what is the medium they are growing onto, what is the effect of the ambient medium having on their properties. So, and this has been not possible before because low frequency instruments have really started to function well in the past 8 or 9 years only. So there was a limitation before, also the number of sources. So LOFAR did a survey in the headache field in 2018, and there was a data release 1. So that was used to search for giant radiogalaxies. Now, giants being really big, even on the angular scale as well as the actual projected scale, it is easy to identify this double in giants. So that's why we were able to identify not a lot, but at least some. So that's the statistics. 14 out of 239 were showing this double morphology, and only 12 are shown here. So that was, so we wanted to find more. So this is, there was a data release too, about a year or so ago. And there, from 239, we went to finding almost 2000 new giants. So we then looked for morphological signatures of restarted activity in these giants, and this was done manually because we need to look at the structures. It's still not possible to automate the whole task. And fortunately, we found a good number of double. The first image, the red color image I showed you is, you can see that example in the bottom right corner. And you can see, again, within double, they all have some unique features. Now, that unique features are coming probably from the environment they are growing into, or the phase in which they are currently in. So here are some general properties I'm displaying about the inner and outer sizes, the redshift of the mu 50 we found. Here is the flux and power. Now I mentioned that 48% are below 100 millijansky. Now 100 millijansky is the radio flux unit, which is really low. And that is the power of this radio LOFAR telescope, that they are going really down to microjansky level noise so that we can uncover more of these very faint sources. So, like I mentioned, this is what we need to do, but for that we needed a big sample. Now that we have a big sample, relatively big sample, we can try and determine the spectral index. And for that we require at least 2 frequencies. So then since we already have the low frequency from the LOFAR, that is at 144, we can look for archival data and do this exercise of spectral index, okay, what is really happening. So this is a double radio galaxy, one of our double radio galaxy. You can see the core, 2 lobes, and the outer ones. And when you make a spectral index map between 2 frequencies, that is 144 and 1400 megahertz, you get this. Now what do you see here? At the center where the core is, the spectrum is really flat. You can see on the scale, it's close to 0.2. And that's expected because that's where the unresolved jets are present and they're continuously injecting and they are not old. And that's why it is flat. And you go outwards, you see a spectral index of 0.6 or 0.7, which is steeper. And then you go to outerwards, they are much more steeper. So they are really old. So this is the first step towards understanding, okay, how old various components could be. To get the exact age, we need more analysis, but this is the first step. And here are more examples. What you see are the contours show you the entire extent of the source, and the color emission shows you the spectral index. I have deliberately chosen to show this because with the archival data, it's not possible to map out the source entirely at all frequencies. You need to detect the same emission across all frequencies. And that is why you're missing a lot. But with archival, that's the best we can do. So again, you can see on the bottom right, the core is really flat. So that's a proof. Now all things have been only done for handful sources in the past. And that's why these studies are first steps towards really getting the numbers right for these sources. And that's another example. So the higher frequency could only detect the inner one. The lower frequency detects the outer lobes, but the higher frequency doesn't detect the outer lobes fully. So that's why we can't make the spectral index map for those regions. So you need really deep sensitive observations even at the higher frequency, where you can map out the source completely. So the first objective was more or less successful, that okay, we were able to show with the archival data. Now we want to go and do a much better job at actually getting the spectral ages, what is really happening, and so that we can do the remaining 3. So for that, we need to go and get more multi-frequency data, combine data across all the telescopes and do this kind of analysis. So we took this sample, LOFAR megaparsec DDRG sample, that's the sample from my 2020 paper. And we put out proposals to various telescopes, including GMRT and VLA. So this was identified from low frequency, so we already have that data. We don't need additional data. So that was the best part of it. Then we obtained GMRT at 650 megahertz. Then we followed it up with higher bands. So basically, we'll have the spectral coverage all the way from low frequency 144 to 10 gigahertz. And that's as wide as one can go for studying these sources. And then we can do the spectral modeling. And this is part of Moshmi's thesis. She'll be carrying out this work ahead. So currently we have data for most of it, and we have proposed for more data, and hopefully this will lead to path-breaking results. So that's the plan, that we get data, analyze, put our heads to it, and obtain a map like this. Now, this is not a radio map. This is not a spectral index map. This is a spectral age map. Like I said, we want to determine spectral index as well as spectral age for every pixel, whatever is possible. So this was possible only when at least 4 frequency radio maps were obtained, where the source was entirely observed in its full extent across all the frequencies. and then you can make this kind of spectral age band. Now you can see that at the hotspot, they are really like hardly less than 10 megayears, so they are very newly injected plasma. And these are the two models. And below what you see is a simulation of how a source would show its spectrum depending on the ages. So the aim is to do something like this, where we see the inner ones showing younger ages, and then we can settle onto, okay, this is really what is happening. So this is a preliminary result of this work. So this is at 144 megahertz. This is at 650. So we were successful in mapping exactly the same structure, what we saw at low frequency. And now the aim is to go on getting the data right for all this frequency, so that we can determine where the break is and which model it fits better. Okay, so that's a work in progress, and hopefully soon you will hear about it from Moshmi. Okay, so we heard of 2 cycles so far. Can we have 3 cycles of activity? That's the question. And the answer is yes. So about 15 years or 16 years ago, Brockhoff et al. Found a source with dedicated observation, not 2 but 3 cycles of activity. Here you can see the outer lobes really at the limit of detection. Then if you see the central one has even more structure of double. Now these are of course much more rarer than double. So there were only 3 known so far, and the exercise which we carried out to find more of these DDRG resulted in finding one more, which I'll come to in a minute. But we were able to map out from the LOFAR survey data the outer extent. You can see here in its full glory that it's much more extended, and we have updated the size. And this is the 4th, the new one, which we found very recently. This was work of Kshitij, who worked with me and Professor Saikya on his MSc thesis. And here you see not 2 but 3 levels of activity. So these are the some properties we are listing here. But again, with archival data, this is the limit which we can do. We can't probe more. So more proposals have been put forth to explore this kind of sources. I guess I went too fast, but that was my last slide. Thank you. I'll take questions if you have any.
Thank you. Yeah, any questions already? I took all of them.
Okay, I probably was the last. It's something I just misunderstood. Maybe it was very, very interesting, but at some point I lost it. Where you show the spectral index band.
Okay. Sorry.
Oops. The colorful one.
I think forward.
You
mean the spectral age?
Spectral age. Sorry. Spectral age. Yes, that was one when I lost the logic. Yeah, here. So I kind of assume that what is close to the center is like young, and at the edges it is kind of old, and here it is the opposite. And so, there is something when I was
okay. So it's very in some sources the radio cores are very, very bright, and it's very difficult to model them. So that's why they have subtracted out in this case. Okay, the example I'm saying, what you see as white, it's actually they have subtracted it out just so that they can do the modeling properly for the rest of the source. Now this is not a restarted radio galaxy. This is a normal radio galaxy where the jets are continuously being injected, and they're depositing all of their major energy at the hotspot, the bright spot, brightest part, and that is where you see the red part. So since that's the brightest and that's being continuously injected, that's the newest part. And that's why the spectral age is very low, 10 megayears. But there is a backflow which is coming from the hotspot that is suffering more losses, and that's why it is relatively older. Like again, okay, there is also mixing of plasma happening here. It's not just one stream which is going and then that's it. There is continuous injection which is happening in this source. So there is a mixture of old and new plasma. So it is in a way very difficult. So there is a third model called continuous injection model, which they are yet to do.
To close factor again, right?
Let me show the.
Goes to the hotspot and then it's like for.
So you see this is the core. The jet is going all the way, creating the hotspot, and then there is a backflow.
Okay, so this stream is not, this is like old.
Yeah, you want the animation. The animation will be- So when it reaches and creates a hotspot, there is that's the extent. It's going to create a shock. That shock is basically the hotspot, and then there is going to be a backflow. And that backflow is very, very less energetic, so it's going to suffer more radiative losses, and that will manifest. That will manifest into the oldness.
Can you go to the little bit in slides with several when you have one of those.
This one,
Yeah.
triple, okay.
Yeah. Triple.
Why don't you
So,
see
but-
outflow?
What do you mean?
Why don't you see this outflow stream, like in the animation you had there? It was like the gas is.
Yeah, so okay, like I said, millions of radiogalaxies are known, and if you look at all of them, you'll catch each of them in the various phases. Yeah,
Actually, next one. So you have three structures here.
Yeah.
So the newest one is
the third one, yeah. Yeah,
But that's the closest one.
yeah.
So on the map, you showed like on slide 34, then the newest is the furthest one.
This one?
Yeah.
This is not a restarted one. This is just a normal radio galaxy. There is no.
Okay. It is within
gave
one
a
period
example.
of activity.
Yes, this is a continuously
Yeah.
active one. There is no.
Yeah.
I mean, this is very hard to do because to obtain multi-frequency data it takes a year, and the modeling takes a lot more time. So, like I said, this kind of maps you will get to see only for 5 to 7 sources so far. So that's why I have just picked one best example.
Okay.
But it has not been done for restarted. That's the point.
Okay. Thanks for sharing. So, anyone?
Yeah, do I assume correctly that every AGN at some stage in their lives have these jets going out? Or some.
So that's the holy grail question, that under what condition AGN
Okay.
produces jets, but only 30% of population has shown to have radio.
But my question is, if there is this radioactivity, for how long it lasts in a
Okay.
single galaxy, and if it stops, after that, how long we can detect these
Okay.
lobes in the radio surface?
Correct. So you understand the problem of determining the ages. Now this has been done for radio galaxies, but that too only 30 or 40 radio galaxies. And the oldest which we have found, the age is about 250 mega years, and the youngest being 1 mega year or half a mega year. DDRG 3-4 DDRGs have been studied. So inner one shows 10 mega years, the outer one shows 40-50 mega years. So on a scale of galaxy's lifetime, this is really small. I hope that answers your. Okay.
Yeah.
I have a question. One is, I know you want to so your goal, and you assume specific goal is to measure the time scale for on of double radio galaxy. So, but is there a theoretical prediction for this the time scale?
Okay, so there are two ages. One, what I'm talking about, the spectral ages is the radiative ages. But if you take environment with some density profile and you say that the jet is flowing with, let's say, 0.3 C, and you just propagate it assuming some density field, you are going to get a number of mega years. That is what we call as dynamical age. Okay, but one thing which is difficult here is to model the environment correctly. You need X-ray and multi-frequency data to multivariate data to get that right. Second is we don't know the exact speed at which these are going, because at the start of its lifetime it might be going at 0.5 C, but as it goes on after a few mega years, the speed might go down. So when we assume a single value, it's like an average estimation. So therefore, even the theoretical predictions, it is tough. What we expect theoretically, the inner ones to be younger, outer ones to be older. But apart from that, there is no thorough theoretical framework designed yet.
What does the simulate? Sorry.
So my second question is, you mentioned that giant radio galaxies, you see them in more sparse environments.
That is what the model, I mean, that is a favored model, but we don't have enough analysis done to explicitly say that that is the case.
Okay, my question is double, do they show a preference with the environment?
Nobody has done that yet. Because
What
as I
is
said,
the
very,
spec?
sorry.
What is your bet?
In my knowledge, they have not been seen in clusters. So they might be in non-clusters environment.
I have two questions. One is, yeah, but what is the difference between spectral age and dynamical age?
Yeah, okay, good. So spectral age is going to tell you the time elapsed since the electrons were last accelerated. So it's sort of a radiative age. Like I mentioned, dynamical, it's more to do with assuming the speed, or if you know the speed from observations and the density in which it is going. So the time it would take, assuming the speed and the density, that is the dynamical age. So there is nothing radiative in it.
The second question is, that you said that it is possibly the merger which causes double,
Possible, yes, yes.
So, but if that is a possible scenario, then when you say that there are three things you saw, so is it possible that mergers can happen?
Yeah, sure. But you see, the merger time scale is on the scale of gigayears. It will be very hard to see the signs of mergers in the present epoch where this is happening. Although we have tried, but we need to do really deeper optical imaging to see if there were signs of merger cells from the host galaxy. So far, there has been no evidence, but it seems likely that if the AGN is starving, how else would it get a fuel or more gas? So a merger is the most likely reason.
How do you, if the merger takes so long, how do you get from these long time scales, which are like driving the thing, if they are, to these very short, or comparatively short, the lifetimes of these jets?
That's the thing which is confusing, because let's say that the merger time scale is about 2 gigayears, but it's not that as soon as the merger happens, this AGN activity is going to go on. In radio galaxy studies, we are still trying to understand under what right condition, is it the mass of the black hole, is it the spin which is causing the jets to start, right? So then it goes to that fundamental question. So I mean, then if the merger is happening, then after what period when the black hole is going to get active?
what goes against the merger hypothesis, at least in my logic, because it's double sources they have on the same line, but if the time scale between these lobes is quite large, then the galaxy is rotating, and I
So
would
there are-
expect that it's
Correct, you're
there is
right.
some angle difference between the outer and
There
inner.
are examples. There are DDRG examples where the initial lobes are here, the inner jets are misaligned. So there are few examples. So that's why some of these models, okay, come up.
Is it something you can compare with simulations? Like you could
Yes,
take
now-
halos,
now-
mergers, how the changes. how-
Correct. So now some simulation people are getting interested in this. And they're trying to do this.
We have 3 questions.
Good, I finished the talk early.
First, is just to clarify, that mergers, there are mergers of supermassive black hole or
Well, when
galaxies.
galaxies are merging, all galaxies have a supermassive black hole at the center. So eventually that
Okay,
will also
okay,
happen.
okay.
Yes.
And 2 more technical questions. Why 144 megahertz?
Okay. Firstly, that's quite low radio frequency, and the part of the radio sky at that frequency was not seen before, and LOFAR brought that capability. GMRT also operates at 150 megahertz, but the dishes, GMRT is dish based. The dishes are not ideal for 144 megahertz at low frequency, because here the wavelength is 2 meters. It's really long. And we know from the synchrotron spectrum that lower the frequency, brighter the objects, if it's going to follow the power law. Okay. So we wanted to look at that part of the sky, that frequency. And again, objects are more brighter. And the aged plasma is going to be brighter at lower frequency. The older plasma is going to be brighter at lower frequency. So and we will miss those sources at higher frequency. So there were multiple motivations to go to very low frequency. Now there are images at 25 megahertz from LOFAR, but that's work in progress.
So it's like purely physical reasons, not necessarily technological one.
No, not
Okay.
technological, yeah.
But this third would be with LOFAR. Is the data improved kind of
Many fold.
every day, basically?
Yes, very, very much, yeah.
Okay, so it's, if I remember correctly, it is observing all the time the whole visible sky, right?
Not the whole. So the field of view of LOFAR is like about 10 degrees at a time. Okay. So they can map out, that's why they can do survey quite fast. For 10 degrees at a time, they can.
Pulling rate that you use to determine the spectral age, it depends on the numeric field, right?
Correct.
Is it measured directly or is it assumed some equipartition argument with the?
Currently with equipartition. Yeah. But if we happen to find some X-rays, then we may not need to, if we find X-rays from where we are finding radio emission, and we find X-rays, then we may not need to assume the equipartition. Then just by the ratio, you can probably put a limit on
The
the.
X-ray would be self-constant or quantum maybe.
Yeah, it probably inverse quantum. Yeah. I think Marit has a question.
It was also about the one that you already have some answers, but anyway, in the local universe, it is known that radiogalaxies and ordinary radiogalaxies are concentrated mainly near the local supercluster plane. And do you have any idea about what's large scale distribution or large scale environment of galaxies or just too early dawn?
I mean, this is what we could work on. You guys are experts on the last few sectors, so, and I can give you my bit on radiogalaxies, but I don't think this has been studied yet. in detail.
Say anything about host galaxies,
Sorry?
morphology of the host galaxies.
No,
Did you-
I didn't follow the question, sorry.
Did you say anything about the morphology of those galaxies, like elliptical, spirals?
Always, most 99% are elliptical,
Elliptical?
hardly any spiral,
But in, you said not in clusters, so in small groups,
probably DDRGs. Yeah.
like giant ellipticals?
Yes, giant elliptical, yeah.
Who have been, they are a result of lots of mergers.
Probably, yeah.
About the spectral indices, they should have been as hard as -0.2 or 0.3. How did they get this hard without double function?
Okay, at the core,
Yeah.
there could be, this, yes, there could be at the core, but there you would see in the spectra, at lower frequency, you might see a turnover.
Yes,
You're right, yeah.
because I mean, if you have just standard optical thing, you shouldn't be able to get
Correct.
harder than 0.5, right?
Absolutely right, yeah. No, 0.3 is, 0.3 is what we sometimes get in jet server, but below that, but the key here is low frequency. We don't know where it might turn over.
Yeah.
So you need to go to low frequency again to get the turnover. Yeah, but most of the other thing is optically thin, like you mentioned.
More questions, comments? People online, you can speak up, or you can write your question to the chat.
Okay. You made it host galaxies are mostly giant elliptical galaxies, and in clusters there are more elliptical galaxies. So, but what is the reason that we don't see these data galaxies in clusters?
We do.
Is it because
Radiogalaxies we do. When I made
Okay.
that statement, that is for DDRGs.
okay. So it's the environment problem.
Yeah.
It is a good question. If they are the product of many mergers, they could be in the large structure.
Yeah, so that's what, I often discuss this with Shishir, but yeah, this is an open thing.
But they could be also in small clusters because they have interact whatever is interbounding. And they remain alone.
Yeah. No, so there are examples in radiomorphology where the morphology has been affected due to a presence of a galaxy group or their location in the cluster. You can see the signs there. So obviously those things are also there.
It's also reminded me also who maybe some of such galaxies be the main galaxy possible. But possible I also different types.
X-ray. Maybe. I'm not sure.
Has anybody done any environmental studies of these double radio galaxies?
I think in Goa, spectra. But if you do some.
But here by environment, what do you mean? Very large environment or local environment?
I mean, say within
Yeah.
local environment, but the cosmic web environment of that.
Like I said, only 100 or so. So,
And
and not that too not limited to very low redshift, like all over. Very hard to do less statistics.
and does the simulation tell us, I mean, do they contribute in our understanding of the morphologies or the energy
Definitely.
distribution?
Definitely. It's just that the major constraint in simulation is that they have to assume a velocity. Second is the environment. Whereas the true picture where these are lying, that if they get some observational inputs that could improve their simulations, make it more realistic.
But there are observational I mean, inputs, right? From X-ray, one can.
No, just I'm talking only with respect to DDRGs.
I see.
When you show the distribution of redshift of the population of Pratik Dabhade in your preparation paper, so it's big, the median is not, it was around 0.4, 0.5. So and then it's decreasing. Is this because of observational bias?
No,
You observe less and less, or it's really that it peaks physically at that?
No, there may not, it's basically the lack of deeper data in optical and radio.
But if you calculate the fraction of the subatomic galaxies over all galaxies, how it depends on the redshift? Is it basically the same, or we expect to see higher fraction of the galaxies in higher redshift or in lower redshift?
I would expect restarted more in the lower redshift regime, less in the higher redshift regime. But yeah, we could try to see taking the entire radiogalaxy population. Yeah, but yeah, I think lower redshift might be more